Okay, now our penultimate lecture in Unit 5 is on matter waves. And this is section 12.3 from your textbook. Now you might think that the title of this lecture doesn't really make sense. And you'd probably be right in that because we've already talked about the wave nature of light. We talked a lot about waves and we understood what waves were and we understood what matter was. Well, now we're saying matter waves, and we're kind of relating both matter and waves together as if there's some sort of wave-particle duality for all types of matter. So we'll get into this. It's section 12.3 from your textbook because it's an interesting sort of theory, and it's another thing that's changing our understanding of our physical world. So by the 1920s, physicists start accepting the quantum theory of light. They start refining these concepts. But then another revolutionary theory gets proposed by a very young French graduate student by the name of Louis de Broglie. And he writes his doctoral thesis on this idea that not only does light behave as a particle, but also that particles behave as waves. So not only do we have light waves that that have a particle duality to them, but particulate matter also has a wave matter to it as well, or wave properties as well. And he proposes, and what he did was actually pretty simple. He just sort of switched around the wavelength of the photon momentum kind of equation, and he proposes that the wavelength of all matter is equal to Planck's constant over the matter's momentum. And he calls this the de Broglie wavelength. Now, it seems pretty simple, but when we were looking at this first, we looked at the momentum of a photon is equal to Planck's constant over lambda. He rearranged this equation and said this is true for all matter. That's what his big thesis was about. So at the time, his professors were like, well, this can't be true. They thought it was really strange, and they didn't even know what to do because he's applying for a doctorate. So what they did was they sent his manuscript over to Albert Einstein and said, can you just tell us if this kid knows what he's talking about, or is he just making stuff up? Einstein read the dissertation, and he strongly supported de Broglie's proposal. So de Broglie was actually granted his PhD not by his professor's opinion, but he was granted it by the opinion of Albert Einstein, which was passed on to his professor, saying, yeah, this kid knows what he's talking about. 6 years after the proposal of the de Broglie wavelength, Louis de Broglie ended up winning the Nobel Prize for Physics for this theory of matter waves. So please copy this down. It's the de Broglie wavelength, the wavelength associated with the motion of a particle possessing momentum of magnitude p, where the wavelength is the wavelength associated with a moving particle, and of course rho is our momentum, and h is Planck's constant. So if a particle has a wavelength, the particle should exhibit interference just as waves do. So to test de Broglie's hypothesis, we have to look for interference involving classical particles. So think about our light experiments where we were looking for interference patterns. Well, we would be able to see interference patterns involving matter. So this goes back to that Dr. Quantum video we saw, where the electrons interacted with themselves, because electrons are matter. They're not light, but they started to have that interaction as well. So matter waves, you can copy the definition. It's the wave-like behavior of particles with mass. And the electron double slit experiment, which I showed you a bit before, showed that electrons did behave and did exhibit interference patterns. Now, this is how this was done is a little bit different than the double slit experiment of light. So it's a little bit different, but here's how it's kind of shown. So during 10 years prior to de Broglie's proposal, physicists Lau and Bragg were developing the theory and technique for the diffraction of X-rays by crystals. So when X-rays scatter from the atoms in a crystal, they form diffraction patterns in much the same way that light forms diffraction patterns when it passes through a double slit or a diffraction grating. So the spacing between the atoms is the same magnitude as both the wavelength of X-rays and the electrons. So it's of the same order of 10 to the negative 10 meters. So that's the spacing between the atoms in a crystal, similar to the wavelength of the X-rays. So that means that it would act as a slit, and it would be able to exhibit what the interference patterns that we would see. So if the electrons have wave properties, then we should see these diffraction patterns. And what we saw was this image here. So 1927, we had physicists Clinton Davison and Lester Germer. They performed an experiment which they aimed a beam of electrons at a crystal target, and the atoms in the target were spaced at regular intervals, acting as a series of slits for the electrons. So just as with the diffraction of light, the Davison-Germer experiment shows that there was an interference pattern when the wavelength of the electrons is similar to the spacing between the atoms in the crystal. Now, what else is interesting about this is you'll notice that the electrons are delivering their energy in parcels. So it's not like a wave that delivers it over a range, but you see these little spots where there are dots, and there are that's the energy of the electrons. So it's not delivering it as a full band of energy, but rather as parcels of energy. So copy down this for matter waves as well. Experiments by Davison and Germer confirmed that electrons exhibit the wave-like property of interference with a wavelength given by the de Broglie wavelength. So let's look at a problem here. It says, in studies of interference with electrons, Davison and Germer used electrons with a kinetic energy of about 50 electron volts, or 8.0 times 10 to the negative 18 joules. The mass of the electron is, of course, 9.11 times 10 to the negative 31 kilograms. So how fast were these electrons moving? So we'll have to use the energy, the kinetic energy, which is 1/2 of mv squared. And rearranging this for v, we end up getting 2ek over m and the square root of that. So the square root of 2, this will be written in joules, so 8.0 times 10 to the negative 18. And my mass, of course, is 9.11 times 10 to the negative 31. So we have 2 times 8 divided by 9.11 times 10 to the power of negative 18 divided by 10 to the power of negative 31. So we have this value. If I find the square root of that, I end up with 4.2 times 10 to the power of 6 meters per second. There's a part B to this question. This part says calculate the de Broglie wavelength of these electrons in meters and in nanometers. So the de Broglie wavelength is lambda equals h over mv. So my h is 6.63 times 10 to the negative 34. My m is 9.11 times 10 to the negative 31. And my v is 4.2 times 10 to the times 10 to the power 6. I have this value in here already, so I'm going to start with this. I will reciprocate it and multiply it by 6.63 times 10 to the negative 34. I'll also then divide it by 9.11 and divide it by 10 to the negative 31. I end up with my lambda as 1.7 times 10 to the 10, negative 10 rather. And to write this in nanometers, I can divide this by 10 to the negative 9, which would simply be 0.17 nanometers. Okay, the next part of this says if the spacing between the atoms in a typical crystal is less than 0.3 nanometers, or similar to 0.3 nanometers, how does the spacing compare with the wavelength of the electrons used by Davis and Germer? So what we can see here is that our spacing is on the order of 0.3 nanometers, and our wavelength is 0.17 nanometers. So because these are of the same order, then, and actually the wavelength is less than the spacing, we would have diffraction, and we would have an interference pattern. So it's actually possible to determine the de Broglie wavelength of larger objects. Now, of course, it's just simply lambda equals h over rho. So if we had a baseball, which has a mass of about 0.1 about 200 grams or 250 grams, and we can throw it at a velocity that would be about, say, close to 30 meters per second. We could substitute that into the equation, but because our h is so small, because it's on the order of 10 to the negative 34, and our velocity is so slow, we actually would have a wavelength that is very small as well. So we won't really be able to notice that wavelength, and we won't be able to see interference because the wavelength itself is smaller than the object that is experiencing that wave. So the results of so we have to prove the de Broglie wavelength using double slit experiments using photons and electrons, and these are surprising and difficult to understand. And the picture of nature at very small scales differs greatly from the classical picture at large scales. Electrons arrive at a screen in single particle-like amounts, but the spot on the screen where they arrive is determined by a wave-like interference pattern. So note, the electrons of quantum mechanics make precise predictions about the results of a double slit experiment, but what they do not give a clear description of is what happens to the photons, electrons, or particles as they pass through the slits and travel to the screen. I want you to copy that note down because that gets us into our interpretation of these results. And this is a big part. This is another one of those unanswered questions in physics. So this slide here has a little cartoon as well. It says here, this is a photon. It says the photon self-identity problem. He says, am I an X-ray photon or a radio photon or a visible? He says, why worry about all that? I'm not even sure if I'm a wave or a particle. So as a result of all this uncertainty, researchers have proposed different interpretations of what happens in the quantum world. The debate still continues over which interpretation gives the best description. And you'll be required to know these different descriptions. So I will go through each of them. The first is the collapse interpretation. So this is the idea, and these are all based on that, remember that Dr. Quantum video. So what happens when matter interacts with itself? So the collapse interpretation is that as the electron leaves its source, it behaves as a particle, but then it spreads out and it travels and interferes as a wave. However, if the location of the electron is measured, it collapses back into a particle and arrives at one location on the screen, just as a particle would. So remember, when you're observing electrons passing through the double slit, they behave as particles. They don't exhibit wave-like patterns. So the idea here is that when you're observing them, they collapse into behaving like particles. So when they're unobserved, they behave as a wave, but as soon as you observe them, you collapse them into this particle-like behavior. So that's our collapse interpretation. The next is the pilot wave interpretation. So here, the electron is just a simple particle, and its motion is described by a single law. The pilot wave interpretation, it basically tries to avoid any of the unexplained collapses that kind of happen. And it describes that the motion of the electron depends on some sort of mysterious pilot wave that knows whether one of the slits or both of the slits are open, and it knows whether it's being detected or not. So if this pilot wave, which is the wave that the electron will travel, if it knows in the future it will be observed, it has it behave as a particle. If it knows that there are two slits that it will come across, it has it behave as a wave and has that that wave-like interference pattern, that wave-like interference interaction. So that's our pilot wave interpretation. Another one we have is the many worlds interpretation. So this one's kind of science fiction in a way, but it basically says that there's a parallel universe that exists for each of the electron's possible states. So the electron goes through both slits, it goes through no slits, it goes through one slit, or it goes through the other slit, it behaves as a particle, it behaves as a wave. All of these things happen, and they happen in basically every time an electron behaves this way, it creates a new universe. We only see the universe where it does the one thing it did in our universe, but there are other universes that exist where it does other things. So this is our many worlds interpretation. So that's that was also in the Dr. Quantum video, of course. You might want to go back and watch that, but that was that's the many worlds interpretation. And the last one is the Copenhagen interpretation. So this one kind of it's sort of like a cop-out in a way, but this was developed at the University of Copenhagen by Niels Bohr. It only deals with the measurement or the results of measurements made on physical objects. So basically, we only talk about the results of the experiments. With the Copenhagen interpretation, it only discusses what we actually do or observe. It does not use any theoretical ideas, such as multiple universes, or collapses, or pilot waves. It interprets only the physical laws in terms of information about actual measurements that are made in a quantum mechanical system. So with the Copenhagen interpretation, it basically says that there are certain questions that do not have answers. What electrons do as they travel to the screen, there is no answer to that. We can only say what happens. We only look at the results of the experiment. So this was the dominant view for most of the 20th century. Now we're starting to move towards some of the others, but honestly, by the time you go through university, things might change because physics is very dynamic right now. So the Copenhagen interpretation, again, basically it's a rejection of all the other theories. It only deals with what we can measure, and it says that there are questions that we have in physics that cannot be answered. So this double slit experiment, it might make you feel that we can't adequately explain quantum physics, but you need to remember that scientific understanding is always evolving, and it's always partly uncertain. Quantum mechanics, as we know it now, explains the results of these experiments very accurately, so it's our best understanding at this time. Things might change in the future, and we have to be open to accept those changes. That's the whole idea of science.